Hi everyone, welcome to this week's ZocMap talk. Today with us we have Lewis, who's going to talk about Lean4 and the Curry-Howard Isomorphism. He's a student in his last semester of a CSC bachelor, so very excited to have a CSC student with us, and so please welcome him.
Thank you all for coming. I want to directly get into it. So Lean4 is a programming language, and I want to quickly explain why Lean even matters. So Lean is really a combination of two things. It's, for once, a programming language, and at the same time, it's an interactive proof assistant. It lets us do some groundbreaking things, such as express mathematical ideas just using code, usually through propositions. And then we can also express these, we can then write mathematical proofs using code to prove these propositions. Furthermore, Lean is, as I said, a proof assistant, so it lets us verify these proofs formally. And lastly, it's just a cool-ass programming language. Lean is really the combination of two mathematical subjects, which is type theory and Lambda calculus. And you sort of know both of these already in their incarnations in programming languages, because type theory becomes the type system or the type checker, and Lambda calculus is really a fancy way of, and a theory about functional programming. Why does type theory matter? Well, type theory is basically a new foundation for mathematics. It is different from set theory and is like more foundational than set theory. Set theory isn't so nice because you can have inhomogeneous conglomerates of mathematical objects, and category theorists don't really like this. Instead, in type theory, everything are homogeneous sets of the same type. Well, it's not really sets. And also there is this Curry-Howard isomorphism, which gives a lot of power to type theory, because it allows us to express mathematical logic in a type system. The big idea here is to use mathematical propositions, so mathematical statements, and express them as types. And the proofs are then the programs that will compile. And since they compile, you know that the proof is correct. So really, mathematical proofs is now just a matter of writing functions between types. And verifying the proof then is only type checking. This is a very powerful idea. Lean is actually being used by mathematicians. Some of the greatest mathematicians, such as Terrance Tao, which is a Fields medalist, uses Lean to formalize his own proofs, which are hundreds of pages long. And by using Lean, he can know that his proofs are correct. And also he mentions that Lean shows the potential how AI can be used in math. There was a recent breakthrough in July 2024 where an AI managed to solve a problem from the International Mathematical Olympiad, where it achieved a score at the level of a Silver Medalist. This is an AI of Google DeepMind called AlphaProof. It is similar to AlphaZero. And really the idea here is that this is a large language model that learned how to write Lean code, and the Lean proof checker can then be used to check whether or not this is valid Lean code, and it actually proves the proposition in question. And so what we can do is we can do reinforcement learning, and we can just have the AI iterate on the code until the proof is correct and the Lean type checker is happy. Probably, as you might be able to see, this system is actually very close to being a gold medalist, so probably this or next year, some AI will be able to be at the level of a gold medal, and maybe someday an AI will meaningfully contribute to solving a millennium problem. Okay, so much for motivation. Let's talk type theory. In type theory, there are really two things. There are terms, here represented by the small t, and types, represented by the big T. And this here is the so-called typing judgment. In type theory, it's all about that. It really means that small t is a term of type big T. And this is really everything it's going to be about. So Lean is just a programming language. So let's try to learn it a little bit. We can, of course, define some objects, and these are, in fact, constants, and we define them by specifying a name, a type, and then a so-called term, which is basically just a value or an expression. We can also leave out the type, and it's going to be inferred. And there is this check command, which lets us ask what the type of an expression is. And you really have here the usual types you have in any programming language, such as integers, strings, and maybe not so common, the natural numbers. There's also this eval command, which lets us evaluate expressions and see what term they reduce to. We can now, in simple type theory, use so-called type constructors to build new types from existing types. One simple example is the product type, which you can think of being the Cartesian product. And then we have terms which are tuples here. Okay? So you can think of this like, so this Cartesian product is then really a new type. And these terms are kind of living side by side. In C++, there's a very easy equivalent. It's just, well, a struct with two fields. There is another type constructor called the sum type constructor, which is not that usually seen in programming languages. It also combines two types, but in a different way. You only need to specify either term. So in the first example, S0, we introduce on the left, and this means we're going to introduce an integer, so we provide a 5. And in the second example, we introduce on the right, so we have a Boolean, and we provide a true. So it's either. You can think of it being an XOR. And in C++, there's actually also an equivalent for this, which is a union with two variants. Well, not quite, because unions don't remember in which variant they are, so you also need an enum, but basically it is a union. We can also define functions in Lean. And this is where Lambda calculus comes in a little bit. So we can define a function, which is called Lambda abstraction. And here, this is the syntax. Basically, you just provide the argument directly after the name. And you kind of can think of this as an argument-dependent constant, where after the assignment operator, you write this constant that depends on this argument x. You can also, of course, use this function and provide an argument called lambda application. And the syntax here is very simple, as it is in most functional programming languages. You just don't use any parentheses, you just write the term directly after the name of the function. Lean is a functional programming language, which means these functions are objects themselves. So we can ask Lean what the type of this +1 object is, and it's going to tell us that the type is nat arrow nat. And this is really another instance of a type constructor. The arrow type constructor, which given two types A and B, will create us a new type, A arrow B, which consists of all functions from A to B. This now inspires a new way of defining this very same function, but with a little bit of a different syntax, where we say +1 is now a constant that doesn't depend on any argument, but this constant is a function. And so the term we provide is now not a constant, but it is the function term itself. Okay? So this is some lambda expression where you map x to x + 1. Since functions are objects, we can easily take them as arguments of another function, and by this get higher order functions. For instance, we can consider this function do twice, which takes an f and an x, and applies f twice to x. This is something you could also do in C++ with std function, but really in Lean this is a language feature, while in C++ this is only more like a library feature. How do we handle multiple arguments in functional languages? Well, it's a little bit different, because usually in programming languages you would work with tuples and do something like this with the Cartesian product of two natural numbers. But in functional programming, we do something called currying, where we have a function returning another function. So the first function takes an argument, which it is the first argument, and then it returns another function, which takes the second argument. And this then allows us to do partial function application, meaning that if we only specify one argument, we can pass around the object which has the first argument fixed. Not only functions are objects, types themselves are objects, meaning that we can declare a variable where we here leave the type out and assign it to a type, like the natural number type. And we can then use this to specify the type of a normal data constant. This is not too crazy because in C++ you can do something similar with a using statement, but a using statement doesn't really feel like an object, right? But in Lean, this constant is really no different from any other constant. But since this alpha is now an object, it must have some type. So the question is, what is its type? And if we ask Lean, it's going to tell us that the type is called type. And now this is the beginning of some brain fuck if you've never seen this before. Since we now have this new type called type, and we can now fully specify our constant definition. And we can now also use this type as an argument to another function. If we once again consider our do twice function, it is kind of specialized to the natural number type. But we can now make it generic by taking a type argument and having the function then be defined on this alpha. And we can also do this in C++, of course, using templates. And here, this template parameter called t really plays the role of alpha. But C++ makes a big distinction between like having normal variables and these type variables. And in Lean, it's all the same. It's just objects. Since type is a type, we can also use type constructors on it. And so we can have, for instance, a function going from type to type. And the example here is the function that forgets about its argument indicated by e underscore, and it always maps to the natural number type. We can kind of now understand what this Cartesian product constructor really is. This time symbol is really just syntactic sugar for writing prod int bool. And we can now leave off the int and the bool, and we will see that this prod thing is actually taking two types as argument and now returning the new type, which consists of all the tuples of integers and bools. This is something you could also do in C++, but very different, right? You would have a struct called prod, and you would have a template over it with two template parameters. And this really doesn't look like a function, but you can sort of think of it like it. Now, type is a type, and we said that all types are objects. This means we can declare a constant that is assigned to type. So what is the type of this constant? Well, if we ask Lean, it's going to tell us it's type 1. A new type. What can we do with a type? Well, it's an object, so we should be able to declare a constant being equal to it. What is the type of this constant now? Type 2. And we can keep on doing this. And this is really something very subtle about the type system of Lean. There is this infinite hierarchy of so-called type universes. There are infinitely but countably many. And really, this forms a hierarchy because each lower type universe is kind of contained in the next one. If we consider type 0, it is a type inside of the type 1 universe. And if you go one more, this universe becomes then a term. This might be a little confusing, but really it just shows that the distinction between type and term really becomes blurry, and it depends on the context. Why would one want such higher order types? What is the purpose of this? Is this just madness? No. It's basically all about abstraction. You're used to working with just type 0, which is also just called type. There the normal data types, such as the natural numbers, string, and so on, live. And also the functions between these data types. But maybe you want to talk about something higher level. You could, for instance, talk about type constructors. We've seen that these are certainly useful. They make it possible to have generics. And so we need to go one layer higher in abstraction and have a new type universe. And now one could imagine, what if we wanted to talk about all type constructors and have functions taking type constructors as arguments and returning other type constructors? Well, then you would be working in type 2. And there are really arbitrary levels of abstractions possible. But you don't have to make use of it. It's just a possibility you have. It's just that Lean is so expressive. So maybe this kind of begs the question, why do we really need this hierarchy? Can't we just have like a single type which rules them all, the type of all types? But this doesn't work. Russell is going to tell you a story about this. You probably all have heard about Russell's paradox if you have taken some logic course, which is from set theory. If you try to construct a set that consists of all sets that do not contain themselves, then you run into a contradiction, because R is going to be inside itself, and at the same time, it will not. So Russell actually, when he discovered this paradox, he invented simple type theory. But he actually then ran into this problem once again, because in simple type theory, you really only have this one universe and don't have this hierarchy. So the real solution to this is not having a single universe, but a strict hierarchy of universes where one universe may not contain itself. Okay, a lot of talk about type theory. Now, real question is, how do we do any math with this? And the idea here is to somehow leverage this very expressive type system. And for this to be, for us to be able to do this, we need to have that mathematical statements are types. So we're going to begin by looking into this by expressing the constructs from propositional logic using types, such as the logical and, or, implication, negation, and the two logical constants, true and false. And for this, we need a new type universe called prop, the universe of all logical propositions. And inside of this, we have types, and the types in prop, they are the propositions. For instance, P of type prop and Q in prop. Well, prop is a universe, not really a type. P and Q are types. And since these are types, they can have terms, right? So what is the meaning of a term HP and HQ, which are of type P and Q? And this is now the crucial idea. A term of a type is a proof. So really this means that our judgment statement, which we've seen in the beginning, now has a different interpretation in the type universe prop. The term T being of type big T really means that small t is a witness to the truth of big T. So having a term of type T means that the proposition big T is true. So proving a proposition is now only a matter of constructing a term of the type which is the proposition. And this then naturally leads to the fact that validating a proof is just type checking it. Lean just needs to make sure that the term you provide is actually of this type. There could be multiple such proofs to a proposition, which is normal in mathematics to have multiple proofs for the same thing, but we really don't care. We have proof irrelevance. We only care about the existence of such a proof. We can forget about the specifics of a term once we have it. It's only about inhabitedness, meaning we only need to know whether or not such a term exists. Let's investigate the system a little bit. So now we consider two arbitrary propositions, P and Q. And now we ask, what is the meaning of a function from P to Q? And syntactically, this really reminds you hopefully a lot of an implication, right? The function arrow looks like an implication arrow. And not only syntactically this is true, it is even true semantically. How are these the same? Well, think of it this way. If you were to obtain a proof of statement P, and the proof is called HP, and you had this function from P to Q, well, then you could supply this HP as an argument into F, since the types align, and this function will then return something, which is a proof of Q. So this is really implication, isn't it? Because you just used a proof of P, you used the implications to obtain a proof of Q. This is implication elimination. It is the same thing as function application. This is also known as the rule of modus ponens. How about implication introduction? How would you create such an implication? Well, you need to do function abstraction. You need to write such a function. And if you write such a function, you will be provided with such an argument, with a proof of P. And now all you need to do to have such a function is to somehow return a proof of Q. And this is the same what it means to prove an implication. And this is now the first instance of the Curry-Howard isomorphism. And it tells us that functions and implications are the same thing. Let's go further. How about logical conjunction? What is here the corresponding type? Well, logical conjunction is really having both terms of a proof, HP and HQ, side by side. And we've already seen a type that allows for this. This is the product type. If we have a product of P and Q, well, then the terms will be tuples containing a proof of P and a proof of Q. And now, using this, and this is another example, of course, of Curry-Howard, but we still use the normal wedge syntax for logical AND. And this is now our first proof. We prove that the logical AND is commutative. And how do we prove this? Well, this proposition, P and Q implies Q and P, really means that AND is commutative. And this is a type. And so all we need to do is to construct this type, provide a term. And this here is the term. It is a function, since we need to prove an implication. And what we get as argument is a proof of P and Q. And now all we need to do is we need to construct Q and P, and therefore we just call the AND constructor and swap the two. So on the left-hand side, we have HPQ.right, and on the right-hand side, we have HPQ.left. And this is a proof. This type checks, and therefore Lean is okay with this proof. How about logical disjunction? There's also a corresponding type we have seen so far, which is the sum type, because logical disjunction just means having a proof of either of them, and that's exactly what the sum type does. And we can also look at a proof of how the logical OR operator is commutative, so we once again need to construct this type, but here it's a little bit more involved. Or constructing a sum type or an OR is simpler, because you only need to provide either a Q, a proof of Q, or a proof of P. But eliminating an OR is more difficult, because you don't have both left and right. You only have either, but you don't know which one. So you kind of need to do a case distinction where you say, where you show that it doesn't matter if it's P or Q. Either way, you can derive Q and P. And these are these two Lambda expressions down here, showing that if you have a proof of P, you can construct Q and P, and if you have a proof of Q, you can construct a proof of Q and P. How about the logical constant true? Well, true is kind of stupid, because true is just simply true. You can get a proof for free. There is nothing to prove. So there is this simple introduction rule which doesn't take any arguments. But it really is introduction only. There is no elimination. This means that you cannot make use of the fact that true is true. It just exists. And there is actually a corresponding type in Curry-Howard, so in types, which is the unit type. And the unit type is basically just this zero tuple, so basically empty parentheses. And interestingly enough, this is a type that is uniquely inhabited, meaning there is only a single term of type unit, which is the empty parenthesis. You cannot write anything else. So there's also just only one instance of true. How about false? Well, false is a bit more involved, because what false is really, it's a contradiction. You should never be able to obtain a proof of false, because it's false. And this really means it's the opposite of true in the way that there is no introduction rule. There shouldn't be one. But in fact, there is an elimination rule. There is the most powerful elimination rule, which says that anything follows from a contradiction. For all propositions Q, we have false implies Q. So if you have a term of type false, you can get a proof of any proposition Q. You might have seen this in the Disc Math lecture, where we've tried to introduce false as an axiom in our system, and then our system becomes unsound, where we can just prove arbitrary statements out of nowhere. So this means you should never introduce false as an axiom, because it makes your logical system unsound. You can think of this elimination rule also in a different way. If you look at this proposition, false implies Q. This is a true implication. Why? Because if you look at the logic table of the implication, then if in the front you have a false statement, well, then the implication is always true. So this means this is a true implication. There must exist a term for it, and well, this term just happens to be used for the elimination of false. This is, by Curry-Howard, the empty type. It's the type that has no terms. It's completely uninhabited. Maybe you're now confused. False. Why? If it's not, if we cannot construct it, why does it even exist? Can you do something with it? Yeah, sure. It still occurs inside of other propositions. For instance, this proposition, P and false is equivalent to false. This is a true proposition. So you should be able to construct this type. And if you now go this direction, well, then you hypothesize a term of type false and show that you can derive this term. Okay? So it still appears. How about logical negation? Well, logical negation is defined using false. It really is defined as being not P is the same as P implies false. How does this make any sense? Well, we can look at the elimination. If you were to obtain a proof of P, HP, and a proof of not P, which is the same as P implies false, well, then you can use this HP as an argument into this function, and you will obtain a false, a contradiction. And this makes sense because you had P and not P. Well, this is a contradiction. We can then use this logical negation to prove statements such as that an implication implies its own contrapositive. But we're not going to look at this proof because it's probably going to confuse you. And this now was the full Curry-Howard isomorphism for propositional logic. Propositions are types, proofs are terms. The logical constant true is the unit type, false is the empty type, implication is a function, not is a function to the empty type, and is the product type, and or is the sum type. Now one could extend this now to predicate logic. We're not going to do this in depth, but the basic idea here is that you can represent unary predicates as a function going from some type, for instance, the natural numbers, to a proposition. And in this way, we can now have statements about mathematical objects or types, like the natural numbers. If you were to be given x of type alpha, then if you had a term of px, this would then mean that the predicate is true for this x. And you could also represent binary relations by having a binary predicate which takes two alphas and returns a proposition. And if you then were to obtain a term of type Rxy, then you would know that then you would have a proof that x is related to y. Then you would also need to introduce universal quantification and existential quantification. And then you could actually talk about some more interesting stuff. For instance, you could prove that the Barber paradox leads to a contradiction. So if we have the type of all men, and the barber is a man, and we have this predicate, shaves, where we can ask if one person shaves another, then we'll see that if we assume that for every man, the barber shaves the man, if and only if the man does not shave himself, well, then we will get a contradiction, since the barber will be shaving himself while he also isn't. And you can easily prove this in Lean. Now that we have predicates, we can talk about mathematical objects. And now really it's just a matter of defining mathematical structures as types, such that they can be used as this alpha in the predicate. And here, for instance, we have a group, which is a structure. And really all we need for a group is some group operation, an identity element, and an inverse function. And now we also have three propositions stating the rules of a group, which is that the operation needs to be associative, expressed as this type, that we have a left identity element, and that we have a left inverse. And really now, if you want to construct a term of type group, what do you need to do? Well, you need to fill in all of these types with terms. So you need to provide proofs that these propositions hold. You need to prove that the thing you're providing is actually a group. And if you're handed a group, well, then these are kind of the fields of your type, and you can make use of the propositions. This is an example of a very lengthy proof for something very elementary. We've only assumed that there is a left inverse, and you can easily prove that if you have a left inverse, there must also exist a right inverse. And this is the whole proof for such a simple thing. And this really shows that if you break down mathematical statements all the way to all its terms, then this becomes very long. And this is kind of a problem, because this is just very elementary stuff. How are mathematicians going to do anything meaningful with this language if they have to write this much code? Well, the thing we've looked at so far was Lean in its term mode. There's another mode called the tactic mode, which allows you to make use of the automated proof writing of Lean. We've seen in the beginning that Lean is an interactive proof system, meaning it's not only a proof checker, but it's able to automatically write some proofs. If you just say which kind of rules it should apply, and then it'll figure it out on its own if you help it enough. We can also define types in another way, which is inductive types. You can, for instance, define the natural numbers in this way, where you say each natural number is either 0 or it's a successor of another natural number. This is really inspired from the piano axioms. And this is really how Lean defines the natural numbers. And you can everything you want to do with it. And you can, for instance, define the operation of addition, where you then always do case distinctions on how you would work with it. So if you add n and 0, you will just get out n. And if you add n and the successor of another number m, well, then you kind of take the successor out and so on. So you can basically do anything you want with this. Now, we're pretty much at the end, and now I just want to give some maybe philosophical notes, more or less, or some practical notes, which is about constructive versus non-constructive math, and the nature of how Lean is a computational logic framework. Let's consider the following question. Is there an x greater than 2 such that 2 to the x is equal to x squared? You can make 2 arguments and 2 proofs for this. Either you make a constructive argument and say, yes, 4 is such a number. And now you have actually the object that fulfills this condition. Another proof would be if you were to know that the graph of the 2 functions in one instance, the one graph is above the other, and then after it swaps, then you know by the intermediate value theorem that they somewhere must intersect, and so there must exist such a value. But then you really don't know which value fulfills this. This is a non-constructive existence proof. And in Lean, as we looked at it until now, is by its computational nature only constructive. Whenever you prove something, you get an example of an object that fulfills this. And constructive proofs are actually very nice because they make a whole lot of difference. For instance, you maybe all know the famous conjecture n equals np. And if we were to imagine to obtain a constructive proof of it, this would not only mean that we know that an algorithm exists that can solve hard problems in polynomial time. No, we would also obtain such an algorithm, which would transform all of computer science. But if we only would have a non-constructive proof, well, then we would know that such an algorithm can exist, but we wouldn't obtain one, and then this wouldn't change much except for maybe mathematicians. But constructive proofs are kind of limited because using classical logic, which is non-constructive, and is the logic you usually use at university, you can prove more statements because you can do non-constructive proofs, which you cannot in constructive math. So Lean can also support this. And interestingly enough, this is only governed by a single axiom, which is the law of the excluded middle. And this one states that for any proposition P, the following holds, P or not P. And this is very intuitive probably to most of you, but this doesn't need to hold. You can do a whole load of math without this. All of constructive math, really. But of course, it is very handy to have this proposition since it allows for typical proof rules where you do proof by contradiction and proof by case distinction. These are all non-constructive proofs. And also, from the law of the excluded middle, it follows that double negation holds. Not P is the same as P. And really, in a sense, this rule, law of the excluded middle, this is what only makes math binary or logic. Without this law, logic isn't really binary because such things don't hold. Okay, I'm more or less at the end. I just want to quickly show how mathematicians now, what they're doing with Lean. So there is this big library called Mathlib, where mathematicians try to formalize all kinds of math, such as category theory. And you can go on this website and then you see all the different theorems they have proven here. And you can already tell that this is some really involved stuff. I don't understand anything of this. But I guess if you have a big enough math background and you know how to do it in Lean, then this is meaningful. And of course, people like Terrance Tao need to make use of this. And there are various people trying to formalize pretty much all of math in Lean. So this is actually something they are striving to, and also to include research mathematics. And of course, for large language models that write Lean, this is a very important resource for them to learn how to write Lean. If you want to try out Lean for yourself, that is very easy. Actually, Lean, I just want to say, Lean is very great software because it was written by computer scientists and not mathematicians. Computer scientists know how to write good software. And for instance, something great they have is this online version of Lean. You just go to live.leanlang.org and you can just write some Lean code. And also they have a very great VS Code extension. You just install the extension, you get a language server, and you can do anything you want to. You get an info view on the right where you can investigate your current state of your proof and what you still have to do, and so on. And lastly, there are some great books if you want to look at this, which is here, this logic and proof, and even better, the theorem proving in Lean4, which gives an introduction on how Lean works. And this is really what I've read. And yeah, this is pretty much all I wanted to say, and I want to thank you for listening. Are there any questions? You're probably already done. Yes?
Why are you personally interested in Lean4?
I think it's just a really interesting programming language. I love programming languages that are extremely expressive. Like when I used to code in C++, then I learned about Rust, and Rust opened my eyes what you can express in programming languages. And I just found this really great. But also Rust has a rather strong type system where you can do a lot of things, but Lean is even better. Lean is the craziest thing I've ever seen. You can express pretty much anything you want and this is not really limited to math. You can write some piece of software, and then you can prove in Lean that your piece of software actually does what it should. Like you can check whether your functions adhere to the specification by constructing proof objects in Lean itself about the code you've written in Lean. So this is really crazy to me. And this is how I initially got into Lean. And now, of course, I think it's very interesting how AI is being used with Lean. Like I've listened to a podcast, I've also linked it here in my slides, which is this YouTube video here, where Vlad Tenev and Tudor Akim from Harmonic, which is a company, talk about how they have a company where they try to create what they call mathematical superintelligence. And they want to basically train an LLM to be really good at math. And what their hope is that they will get so good at reasoning in general, because math is just about reasoning, that they can also use this AI in other fields of science, because it's just an AI that's great at reasoning. And what is also interesting is that since they're using reinforcement learning, there really is no upper limit to the intelligence of the system. Because if you usually train LLMs, you are limited in the intelligence of the system by the quality of the data, right? But if you do reinforcement learning and just use the Lean proof checker as feedback, whether or not it produced good output, well, then you have infinite amounts of data, because you can always just ask the proof checker what it has done. So this is very interesting. There's no upper limit to training it, just like in the case of AlphaZero. Any other questions? Yes? Fermat's theorem is probably the most famous one, I guess. And you could maybe investigate what kind of proofs Peter Scholze and Terrance Tao have proven. But I don't know. This might be over my head and yours also, because it's just very intricate mathematics about some subject. Yes. Alex?
Assisted proof checker. How does Lean determine in which order to apply rules? I'm guessing this is randomized algorithms. It's not anything deterministic.
That's a great question. I'm not quite sure. Of course, it helps if you give it in the right order, and I think it's kind of limited. Because as a combinatorial problem, trying out all combinations is probably very bad in its computational complexity. So I think this is rather limited, probably. You more or less need to give the right order of how to apply the rules. So you kind of still need to know how the proof would follow, but you can get rid of writing out all the terms. That's kind of the idea of tactics. Any other questions? Otherwise, yeah, thank you for listening, and we can move over to the apéro, I guess.